So when we talk about the Hall effect, there's something like the cross field, which means there is a E field and B field which are perpendicular to each other. And here, the E field is generated by the particle, and due to the Hall effect, it can tells you two things. One is that the Hall effect can tell you that the moving particles are positively charged or negatively charged. And the second one is you can calculate the number of such carrier per uniform. The later one is simpler because finally we can derive this equation, and actually the B, I, V, and L and E are known because the external B field you suppose you know the current going through this wire also unknown, and the voltage from this side to this side is also a known. You can just measure it with a multimeter, the length of this wire and also the elementary charge. So all are known value and all measurable. So that due to this measurement result, you can calculate the charge density. And the second one is it can tell you whether it is electron going up or positively charged going down. Because at the beginning, it assumed that the electron moving, at the very beginning, we assume the moving particle are electron, which means when the current going down, which means the electron going up. How about if we assume positive charge going down? What will it be? So if maybe we recall what it is about the electron. If it is electron going up, which means V is pointing upward and B is going into the page, so which means V pointing up and E pointing inside. So V cos B should be pointing to the left, and Q is negative. So Q times V cos B should be pointing to the right, which means the electron will go into the right side like this graph. If we assume the moving particle are positively charged going down, so it will be something like we have positively charged particle going down, which means V is pointing downward. Of course, this is not true, but it is an argument to state why it is negatively charged. So V is pointing downward, and B also point into the page. So V cos B, V pointing downward, and B. So V cos B should point to the right side. V cos B. And Q is positive. So Q V cos B also pointing to the right. Q is positive. Which means in this case, the positive charge will go to the right side. Something like this. The positive charge will go to the right side. So the induced negative charge go to the left side. In this case, what we measured should be opposite to the practical case, because according to the experiment, we can measure the voltage between this side and that side. And we know that if the current line going downward, the potential on this side is higher. But if the moving particle are positively charged, it will be opposite. So this tells you that this experiment tells you that it cannot be a positive charge going downward. That's what I forgot to mention in the last lecture. Here we talk about the crossing field. We have not crossing field. We have a magnetic field, and the magnetic field is pointing to inside. We can't see it yet. Pointing inside pointing into the page, or well, suppose this is a positive charge and this is going into the page, so V cross B pointing to the left. So this particle will be in a circular movement, circular motion. And this is the Lorentz force equals to ma using the circular motion equation. So we know the acceleration is v squared over r, and this is Newton's law of motion. F equals ma, so we have this force equals ma. So we know that the radius of the circular movement is something like this. So we move on to the cyclotron. Cyclotron is the first type of the particle accelerator. So later we will talk about the synchrotron. So cyclotron in Chinese is called 回旋加速器. Okay, so so we can see the graph on the left. So here we have a disk in light blue. So in this disk there are uniform magnetic field pointing out of the page. You can see a lot of green dots. And as I mentioned just now, if the particle enter the B field, and then you will have a circular motion. So we try to separate these a bit. So there is a gap here. In this gap, there are no magnetic field, and instead there will be some electric field. But the electric field will be pointing to the left and pointing to the right alternatively. So it is something like, if there is no gap here, it will be something like circular motion. However, now just assume this part is not exists, and then it will go in a half circle, and then it enters this region. Then the E field pointing to the right, assume the particle is positively charged. Then in this case, the particle going here will have an acceleration pointing to the right. So when maybe I can try to enlarge it a bit. Okay. So when the charge going to here, so here you have an E field pointing to the right, so that the particle going from here to here will accelerate a bit. Then it enters the right hand side again, and then it will be another circular motion. So it go into another half of a circle, and then go into here. Then here the E field pointing to the left, so it accelerates again. Because if it is a circular motion, the velocity or the speed of the particle remain unchanged, because the force is pointing to the center of the circular motion. So V is always constant. But here, for this half, the speed remains unchanged, and then accelerate a bit so that you can see that if the v increase a bit, r also increase a bit because mq and b remain unchanged. So if v increase a bit, r also increase a bit. So in this case, the particle will going spherically. Actually, what we need to set is the frequency for changing the E field. The key to the operation of the cyclotron is the frequency f, at which the proton circulate in the magnetic field, and that does not depend on the speed, must be equal to the fixed frequency f of the electrical oscillator, which means when the particle go to here, the E field should point to the right, and after that the particle goes to here, the E field should point to the left instead. And go to here, E field point to the right, point to the left, point to the right, and then the particle will become faster and faster, and it carry more and more energy in it, more and more kinetic energy. So the frequency should be something like this to make sure that the particle can be accelerated. Otherwise, if it does not satisfy this equation, the particle will get lost somewhere. So, and finally, going to the here, then the particle will split out. Okay. So I think, well, I don't think I will need to explain it here. And actually, for the cyclotron, it has some limitation. The speeded particle can only have energy less than 50 mega eV because you need to generate a magnetic field in this whole disk, which means you need more power so that the B field can be generated in the whole disk. And you can see that the speed is proportional to the B, to the magnetic field. The mass is fixed, the particle mass is fixed. The R depends on how large the disk is, it's also fixed. And or maybe you can make a larger disk, but if you make a larger disk, you have more difficulty to provide the same magnetic field in the disk, you know. And of course, the charge of the particle is also fixed. So suppose Q, R, and M are fixed. So we want to make the magnetic field larger and larger so that the output speed is larger, and so as the kinetic energy. So as we need to fill the whole disk with the magnetic field, we cannot accelerate the particle too much. So we have the cyclotron, which is something called the 同步加速器. Okay, so in this case, I don't have a graph here, but actually the cyclotron is something like a ring rather than a disk. It will be something like I'm not sure whether there's a graph on the textbook, but actually here we only have the B field only inside this ring rather than in a disk, so that the energy can be more dense, which means we have a larger magnetic field, so that we have a larger B, so that the velocity can be larger. In this case, the magnetic field B and the oscillating frequency, instead of having fixed value as the conventional cyclotron, are made to vary with the time during the accelerated cycle, which is done properly. So in this case, we can provide a larger magnetic field, but the control of the E field, B field will be more maybe the E field is more complicated. It's more complicated, so that the particle always accelerate in this ring rather than on a disk. So in this case, the proton follow a circular, not a spiral path, thus the magnetic field extend only along the circular path, not over some this is really large, 4 times 10 to 6 meters square. The circular path, however, still must be large if high energy are to be achieved. So up to 2019, the beam is then injected to, so this is from the Wikipedia, you can check it on this link, on this page, the proton synchrotron, which accelerate the proton to 1.4 GeV, followed by the proton synchrotron, which pulls the beam to 25 GeV. So it is something like 500 times larger, 500 times larger. So you may have a question, why do we need the particle accelerator? Why do we need a particle accelerator? It's something like, so the physician would like to know what is the fundamental building block of the universe. So in the past, we tried to know, maybe there are some elements, hydrogen, helium, and so on and so on. So then we know there is something like the atom. So what is inside an atom? Then the physician can try to know that, we try to disassemble it, and then we know that there are some proton, we have some positive charge with some mass, something like 1.67 times 10 to minus 27 kilogram, something like that. And the proton, the proton and also the neutron has all have similar mass, but it does not have any charge. And also in the atom, we also have electron, which has a negative charge. So within an atom, it is electrically neutral. And for different elements, there are different numbers of proton, neutron, and electron to construct the whole world. So can we find the even smaller building blocks? So we try to use the particle accelerator to do this stuff. You can imagine, if you want to disassemble your phone, you can do it gently. So you try to find some tools, something like a screwdriver, and so on, and then you spend half an hour or 1 hour to disassemble your phone, so that you can, you open it and then you find it, there's a PCB and there's some chips, some sensors, something like that. And everything is good, but it is slow and you don't really know what is really inside a chip or something like that. But another way is to disassemble your phone faster is something like, or maybe I could put it backwards, is to pick up your phone and smash it on the ground. Then it drum. Then you can buy a new phone, of course. But in this case, with this collision, you suppose you can find some smaller element of your phone rather than disassemble it gently. So for the physician, they try to do this kind of crazy stuff. They try to accelerate the particle and then they collide together. So they may generate some even smaller fundamental building block. So we can build the standard model of the particle. You may check it. Well, I think I have put it on chapter 21. Something like here. So actually, within a within a proton and electron, it's actually built up with quarks, and suppose you use some high energy proton collide with each other, then it may split up with some up-down quarks, something like that. And for different level of quarks, this is the first generation, second generation, and third generation. You can see that it needs different kind of energy to disassemble a proton or a neutron, something like that. And it's something like 2.2 mega EV. This is something like 1.28 giga EV, and this is already 173 giga EV. So even for that Cyclotron, we may not disassemble this type of quarks. And this one is the Higgs Boson, which is very famous in a few years ago, because it's called the particle of God, because this is a very crazy idea. Because imagine that the particle itself does not have a mass itself, or the mass of a particle is not referred to itself only. There are some interaction between the quarks and the Higgs boson, and the Higgs boson will give some mass to different types of particle. So that is like the God, oh, I give you some mass. So different kinds of quarks will have different mass, something like that. That's why we call the Higgs boson the particle of gods. Well, so we may come back. So we have an example. Suppose a cyclotron is operate at an oscillating frequency of 12 megahertz and the radius equals 53 centimeters. What's the magnitude of the magnetic field is for deuteratron, one proton and one neutron, to be accelerated in the cyclotron. The deuteratron mass is m equals something like that, which is 2 times the proton. So So we know that B equals 2 pi m F oscillate over Q. So you plug in the values. 3.34 times 10 to minus 27 times 12 times 10 to 6 over 1.9 times 1.6. 1.6 times 10 to minus 19. So it is something like 1.57 Tesla. Okay, let's move on. So for B, what is the resulting kinetic energy of the deuteron? So V is R times Q B over M, which is 0.35 times 1.6 times 10 to minus 19 times 1.57 over 3.34 times 10 to minus 27. So it is something like 3.99 times 10 to minus 7, which is really fast, which is which is something like 13% of the speed of light. So for the kinetic energy, 1/2 mv squared. So it's something like 1/2 times 3.34 times 10 to minus 27 times 3.99. Times 10 to 7 squared. So it is 2.7 times 10 to minus 12 joule, and then you divide it by 1.6 times 10 to minus 19, it will become 17 mega eV. 17 mega eV. So this is what we mentioned for the cyclotron, which is smaller than 50 mega eV. So, any questions up till now? The frequency is fixed, but so you need to control this frequency. This frequency will determine how fast the particle can be. QIM QB. So this is the T what we mentioned in sample problem 28.3. So T is this term. T is this term. This is not related to the. This only related to the mass, the Q and B. But for that case, M, Q, and B are fixed. So if it goes for a longer path, but actually the speed is faster. So the speed for going from this to here or this to here is the same. So the frequency here should fix. So the E field. Well, but I think that may be a problem, but well, but this gap is very narrow. This gap is very narrow. So, well, it may be some difference because well, the particle going from here to here and here. This one is more or less negligible compared to this one, but well, they must consider this. Well. Yeah.一周吧。Because it's go from this side, maybe this side, we call it 1 to -1 to 1. So 1, -1, 1 is a cycle. Any other questions? Yeah. That's why when the particle go to here, the E field should point to the right if it is positive charge, and going to here, the E field should point to the left, so on and so on. So let's move on. Okay. So at the beginning of this chapter, we have the Lorentz force, which is related to a moving particle, moving charge particle, moving in the magnetic field. So here we talk about a wire. It has a current going through it. So for a wire with current going through it, which means there are some charge particle moving on this wire. So in this case, there will be also a force acting on this wire if there are perpendicular magnetic field. And actually the force FB is something like I times L cross B. L is the length vector. Maybe you can cut it into very small pieces so that it will be something like EL for every small part of the wire, and it cross with the magnetic field, times the current, it will become the force. And actually here we can see that suppose the current is going to the top, which means L is also pointing upward, and the B is pointing out of the page. So L cross B is pointing to the right. So in this case, the wire will be something like this. And for the right side, the current going down, so I cross D will point to the left, So the wire will be something like this. If a wire is not straight, field is not uniform, we can imagine the wire broke up into small straight segments. So we can break it into segments so that for every infinitely small length and cross with the B field, and then we can integrate together. So something like what we done in the chapter 22. So we have a sample problem. Okay, a strict horizontal length of copper wire has a current I equals 28 ampere through it. What are the magnitude and direction of the minimum magnetic field B? Need to suspend the wire, that is to balance the gravitational force on it. The linear density is 46.6 gram per meter. Okay, so for this wire, it has two forces acting on it. One is the gravitational force, which is small m times g, and another is the force. This force actually is also the Lorentz force. So in this case, I L B equals mg. So maybe let's check it first. L is pointing out of the page. And the magnetic field is pointing to the right. So we have L cross B pointing upward. So FB really point to the top, and mg of course point to the down. Okay, so we want to find B. We want to find B, which is equal to mg over IL. And actually what we know is m over L, g over I. So we have 46.6 times 10 to minus 3, because the SI unit for mass should be kilogram rather than gram. And this is 9.8 meter per second square, and divided by 28. So the magnetic field is 1.6 times 10 to minus 2t. Well, actually for this question, it asks you to determine the direction of the magnetic field by you, but well, this graph already shows it here. So actually, we know that the gravitational force is pointing downward, and So the FB is pointing to the upward. So you need to think the direction of B with the direction of L and FB. It's something like you do the convolution, so you also have B convolution. Okay, so we talk about the torque on a current loop. Torque on a current loop. So just now we know that if a wire has a current and then there are a magnetic field which is not the same direction with the wire, then you have a force. So here we have a current loop. So of course there will be some here some E field pointing to the right. This is the north pole magnetic and the south pole magnetic. So that there is a B field pointing to the right. In this case, there are some force acting on this loop. However, we know that for this wire and this wire, the direction of L vector and the magnetic field is either the same or the opposite. So when they have cross product, the answer is 0. However, for this side and that side, for this side, I going to this way. I going this way, and B pointing to the right. So I cross B. So this F pointing upward. And on the contrary, for this wire, the current going this way. So I cross B pointing to the downward. So in this case, this wire loop should rotate with respect to this axis, because this is something like a fixed axis, and then this go up, this go down, so that it will try to rotate clockwise. And actually, we can calculate that something like this. So this is a cross section of this of the right hand side graph. Suppose the wire loop is something like here, and this is the normal vector of this wire loop, and then it has a angle between the normal vector and the magnetic field, which is theta. So in this case, we have F1, which is this one, and also we have F3, which is this one. Actually, they are the same in magnitude, but the direction is opposite. For the torque, we know that it should be equal to the length here times the force. The magnitude of the force is the torque. So in this case, I'm not sure here. So the force would be something like the force will be something like AB plus sine theta. Well, so we know that FB is IL cross B. And actually, this wire is perpendicular to the magnetic field. So F1 should be ILB. And also for F3 is also ILB. So for this one, this is small b. This is small b. Maybe I just erase this. Erase this. Actually, we need to calculate. We need to calculate this. This will be something like 1/2 of b sine theta. Because, well, maybe I can draw it here. Something like this. This is theta, so this is also theta. And this one is b/2. So this one is b/2 times sine theta. So the torque referred to F1 is something like ILB times b/2 sine theta. And so as F3, because this is pointing to the top, this is pointing to the down. So for the torque, refer to this axis, they are in the same direction. In the same direction, should be pointing inside the page. So pointing to the inside the page because we use the right-hand rule. So the torque is something like this. So the vector of torque should pointing into the page. And actually, the magnitude of these two are the same, so we multiply it by 2. So these 2 and these 2 are cancelled. And L times B is the area of this loop. So we have AB. We have AB and also I sine theta. So where does N come from? So actually, for this loop, you can have more than one loop. You can have capital N loop, is the number of turns in the coil. So that the force is N times larger. And the torque is something like this. Actually, you can write it as a cross product. Well, something like the cross product here. Which is something like the area vector cross with the magnetic field. Then A, which is A cross B. A cross B, yeah, pointing to the inside the page. N is the number of turns in the coil, which means that this is not one wire. This can be with N loop. So we know that
coil of area A and turn and N turn carrying a current I in a uniform magnetic field will experience torque given by mu cross B. Actually, it don't use the A cross B, use mu cross B. Mu is defined as the magnetic dipole moment, which is generally used in physics and something like the quantum mechanics, something like that. Remember this mu. When I prepare chapter 23 today and yesterday, I see a lot of mu, which is something really difficult. I actually don't know what it is, but when we talk about the quantum mechanics, there are many something like the magnetic dipole moment, which is something similar to the electric dipole, as we talk in chapter 22 to 24. They say a similar equation. The torque is something like the dipole moment, no matter magnetic or electric. The dipole moment cross with the magnetic field or the electric field, and the form for the energy is something similar. Actually, the magnetic dipole moment is defined as mu equals NIA, which is the current going through the loop times the area and times the number of turns. So this is an important parameter in physics, although I'm not a physics guy. And actually, the direction of the dipole moment, of the magnetic dipole moment, follows the right-hand rule, which is something like if the current is going counterclockwise, so that the dipole moment onto the downside, and if the current going this way, this is counterclockwise, this is clockwise, and so this dipole moment onto the pointing upward. So actually there are some potential energy, and actually if you need to change from this state to that state, you need to have some work done, no matter it is a positive work done or negative work done. You need to have some work to make it from this state to another. And actually it depends on the angle between the dipole moment and the magnetic field. So here we have another example. So for part A, a circular coil with 250 turns and area A and current of 100 μA. The coil is at rest and in a uniform magnetic field B, with its magnetic dipole moment initially aligned with B. So B and mu are in the same direction initially. In the figure, what is the direction of the current in the coil? So it will be something like, this is mu, so this is something like that, something like this. Because it is difficult to express, because it is 2D.
because this is 2D, you can imagine it is something like this. Something like this. Okay. So this is the question for part A. So for part B, how much work would the torque applied by an external agent have to do in the coil to rotate it 90 degrees from the initial orientation so that mu is perpendicular to B and the coil is again at rest? So actually here we have WA equals U 90 degree minus U 0 degree. So it is something like mu B sine 90 degree minus negative mu B sine 0 degree. So it is nothing but mu B negative. Should be negative. Okay, so so mu B is NIAB, and now we know that N is 250, I is something like 100 times 10 to minus 6 times area 2.52 times 10 to minus 4 times B is 0.85. So the answer is 5.36 mu J. Another dipole by the agent. Okay. Done by the agent. Yeah, it should be negative